right. Thank you very much for coming to the workshop today. So I'm Hailong Chen from mechanical engineering. But for your information, I actually am a chemistry PhD. So happen to be working in the mechanical engineering department. So this is my group, okay, at Georgia Tech. What do? So we do material design new materials, new compounds, mostly inorganic solid materials, and the applications including recent years mostly battery materials, but we do a little bit of catalysts and structural metals and alloys. Okay, and our major technique expertise and tools are building different kind of in situ and operando tools based on X-ray and neutron. Okay, hopefully they are going to show you just two examples, how we are using operando and in situ categorization in our research. All right, so I'm going to show two of our projects. One is the design of high energy cathode materials for sodium-ion batteries, where we combine in situ and operando XRD. And in the second project, I'm going to introduce our work building an in situ XRD for hydrothermal synthesis and a few more other things. All right, so since we assume that the audience here coming from different backgrounds, so I just want to give a very short background about batteries. So batteries like lithium-ion batteries that we are using in our cell phones, we have cathode and anodes. We are layer materials, and lithium ions are substitution the cathode and anode through the liquid electrolyte. That's where what happens inside the battery and outside is electron traveling, which gives the energy to light up the Bible or your cell phone. All right. So what people working in the battery field care is first understand how those cathode and anode materials work. With that, we could use XRD to look at the structural change, crystal structural change, including the more obvious, change, and more subtle, low quality change and defects and so on. Okay. So that's the connection between the actually diffraction acceleration and battery research. So batteries can be used in many applications, as you know, from very low power, small power devices to very large energy storage units, such as the buffer units or great energy storage. Okay, and or for electric vehicles. You can imagine that with different applications, of course, people look at the different aspects, different merits of batteries. For example, for more expensive batteries, the batteries that implanted into people's body, like in the pacemaker, people don't care about too much about the price. People care about the stability. Okay? But for large-scale energy storage, people don't care about the energy. People care about the cost. They must be very cheap. So to imagine that for different ending applications, you have to wisely choose the battery chemistry, which kind of battery is better suited for your application, right? Okay, today I'm going to introduce one of our projects, which is targeting the grid storage, the large-scale energy storage, where the cost is an issue. So we study sodium-ion batteries. I mean, lithium-ion batteries is probably more familiar with everybody. We use it every day. But sodium-ion battery, I can tell you that it's very similar to lithium-ion batteries, just to replace lithium with sodium. Okay. Of course, the major benefits of using the sodium-ion battery is that sodium is 1,000 times more abundant in the Earth's atmosphere, right? So in principle, sodium-ion batteries could be much more cheaper than lithium-ion batteries. Unfortunately, this is not the fact now yet, because now the cost of the battery is not just the material, the battery cost. So, but in long run, I think that we can safely say, if the, we have all the equal advantages in manufacturing for lithium and sodium-ion batteries, then sodium-ion batteries will be much cheaper. Cheap. So, okay, so in this project, we are trying to develop high energy electrode for sodium-ion batteries. A little bit of background is that sodium-ion battery is actually invented or first studied almost at the same time as lithium-ion batteries in the 1970s and early 80s. But just because lithium-ion battery has much better performance, so it stands out, right? So sodium battery is actually kind of left behind for many decades, but now people start to revisit sodium-ion batteries because of their cost advantage. Okay, so the people want to use sodium-ion batteries, but also people are expecting kind of similar level energy density for sodium-ion batteries to the popular lithium-ion batteries. But what is limiting the energy density of sodium-ion battery is currently on cathode side. Okay, people mostly use layer oxide as cathode. They have very high theoretical capacity, but practically people can only take 40 to 50% of the theoretical as the practical capacity. So there is a gap. So our aim is to understand this gap. Why do we have this gap, and how to mitigate this? All right. So again, this is the structure. So we focus on the cathodes, the layered material, and so this is today's topic. We focus on XRD, and now I have to apologize. I have to skip a lot of details of the materials with limited time, but I try to be outside deliver the most important information. So for layered oxide cathodes for sodium batteries, most often seen there are two structures, O3 and P2. Okay. If you look at diffusion paper, 1,000 papers per year, and I guess 90% of the cathode people are focused on these two structures. Okay, they are different, but the difference is very little. So here in the O3 structure, the sodium stays in the octaedral site, and Y is O. And in the P2 structure, the sodium stays in the prismatic site, which is a little different. Okay, and in our past research, people gradually identify that P2 maybe is more promising structure because it delivers higher energy, although it's not theoretical yet. P2 is in general better than O3. Okay, and this is a sort of famous paper published in 2012 by a Japanese group. This paper is important because from this people in the field see the hope that the energy density of sodium-ion battery can match lithium-ion. This is the first material shown us that. But this material has a serious problem of cycling. If you cycle this material more than 20 cycles, then the capacity drops a lot. Why? Because seems I missed the slide. Okay, please let me jump to this slide. Yes. So this is a paper published a few years after the Japanese paper. So Claude Dalmos and his group showed that this is the easy XRD. Okay, so the XRD, you can see the structure change of this material from, and this side is the voltage curve. When you charge the battery, you increase the curve, the voltage from 1.5 to 4.2. This is the voltage curve. And meanwhile, you check the XRD. So this is the XRD, or you can call it operando for long battery. So you can see obviously there is a phase transition when you charge the battery to high voltage, like 3.5 or 4 volts. Here the structure is transitioning from P2, the original P2 structure, to this structure, and this is O2. Okay, and this is a phase transition, and this phase transition unfortunately is bad. Okay, why it is bad? Okay. I have to, limited by time, I have to say very simply. So physically, there are many ways to conduct this P2 to O2 transition. Okay, they are equivalent from the physiology side, but physically it can happen in different directions. Okay, it's like if you have a pile of pennies piled together, if you push it, you can push it to different directions, right? But they are equivalent. It's just tiny. But you can imagine that this kind of timing happens in the particle. Inside one particle, you can have two different sliding against each other, right? You can imagine that with that happen, you have a lot of dislocation. Okay. That means one phase transition actually can create a lot of dislocation just because of different sliding direction. Okay, like shown here. And this happens in every cycle, charge discharge. And if it happens handles time, gradually you break like this, you can have the bulging out edges, and later on have the micro cracks open up. So basically the better the cracks. Okay, and this is because this kind of phase transition. Okay, so phase transition is bad. So our strategy is to try to eliminate this phase transition possible from P2 to O2. We want to eliminate that. So how to do that? Again, I skip the details, but I just tell you that we got inspiration from lithium-ion battery materials. Okay, from some working very high performance lithium-ion battery materials to get an idea. We want the transition metal layer of the layer oxide to be more heterogeneous. We want to introduce more heterogeneity in the transition metal layer. But how to introduce more heterogeneity? So we propose to use lithium because lithium is very different from transition metals used. Manganese, nickel, cobalt. They are transition metal, but lithium is one class, manganese is 4 parts, cobalt is 3 parts, right? If you have some, like very heterogeneous lithium there, it works like thin structure, so that you don't very easily to have this kind of phase transition. The phase transition takes place by sliding the oxygen layers. Okay, but if you have some pins here to pin up these layers becomes not very easy to slide. Okay, so that's our strategy to stop or eliminate the phase transition. Okay, so to verify if our hypothesis is correct, so we designed many compounds. This is the first one. Okay, so again, you have to skip the details because there are a lot of other limitations. You have to keep the charge neutral, and you have to limit the amount of sodium in your formula in a certain range. Keep it in P2 because P2 favors certain range, and O3 favors the other range, and also other considerations. So this is the first model compound that we designed. Here we want to put 20% of lithium in the transition metal layer, which is majorly manganese 4 class. Okay, so we want to synthesize this material and test it in batteries. So well, this is our theory. We want to put the lithium in the manganese layer, but we don't listen. The elements just don't listen to you, right? You mix the starting materials together and put it in the crucible, in the furnace, and fire it up, and they go whatever they like, right? So how do we control them? So here we can get some help from in-situ XRD for synthesis, right? Okay, so we have fortunately we have this in-situ XRD for synthesis in our lab. So as we have this furnace and power furnace, which can go up to about 1100 degrees C. So then we put the starting material in the design ratio into this in-situ XRD encoder, and we heat it up. You can see that the phase transition is actually kind of complicated. So this is the starting material, which are basically carbonates, and from 400 degrees C, we start to see the oxides, and this oxides, I can tell you this is lithium layer hydroxide, layer oxide, okay? Because lithium has higher reaction activity than sodium compounds. So lithium first form a layer compound, and then about 500 degrees C, you can see the lithium phase and sodium phase both form layer phase, but they are not mixed. And later on, they start to mix, but they are forming a in our paper, we thought it's O3 phase, but later on we figure out this is not O3, this is the P3 phase. They are very similar. So this is the P3 phase. And you keep increasing temperature, then this P3 phase transition to this P2 phase, which is our target phase. Okay, you can see that this transition is kind of complicated. And if you keep heating it up more than 950 degrees C, it transition to another phase. We don't know what that is. We cannot be indexed, but I guess it's all the runtime phase. Okay, and once you form this phase, even you cool it down, it goes back to the P2 phase majorly, which is because this is a somewhat stable phase, but you still have some residues here, which are bad. So this is the XRD form. This is the tell us that if you want to have a pure P2 phase, which is what we want, you better fix your synthesis temperature in this range. Otherwise, you get better. Okay, so this is very informative. You can imagine that if we don't have this XRD in our lab, our students have to do handle experiments to test out, right? What is the right temperature and what is the right region? Okay, with this, within a few days, we figure out. And we get the pure phase P2 with using this situation. Okay, and amazingly, it worked very well in the sodium batteries. Okay, it delivers 222 milliamp hour per gram capacity in the first cycle. You may not have idea, what this is, but I can tell you that the theoretical is 235. We get 222, so that's 94% of the theoretical. And remember that I mentioned most of the materials only works at their 50% of theoretical. So this is already a big step up. And also for lithium-ion batteries, most of the cathode materials only delivers 140 to 180 milliamp hour per gram, and we can deliver 200. So we see lithium is possible. Okay, this result is good, but for research, what we are more interested in is why do we have this? Can we make that? So first, we want to this is comparison of our capacity and the similar material published before. So our capacity is the highest at the time we published a paper in 2018. So we first need to verify if this material is really what we design. Okay, if we really put the lithium in the sodium in the attractive layer, okay, that's like I show here. And we use synchrotron XRD, high resolution, and the refinement. Find a little tiny peak here, which is the superstructure peak for the honeycomb ordering the transition metal layer. But this is just a science, not quantification. We know that it's there, but you cannot quantify this because the lithium is light element. It's not good actually scattered. You cannot quantify those small amounts actually evenly. So we use solid state AMR to quantify it because lithium at a different crystal figure site do have very distinguishable signals in solid state AMR. Again, here there are a lot of AMR details, which probably is not, there's no time for it for today. But our conclusion is that we have 90% of lithium we put in some material goes into the transition metal layer. Only 9% of lithium stay in the sodium. Okay, so just use more percent, but it's already that we can do. Right? We can see that we mostly obtain what we design. Okay, and then the next step is to verify, with this material that we designed, did we actually eliminate the P2 to O2 phase transition? Okay, with that, we need to check it with into XRD. Okay, and into XRD for battery actually has a long history. You can see that the paper already published in 1992 by Jeff Dang, and he has his own instrument with the lab, also with the broker. I think it's very early models, 3000 or something. And this is the model from gallium nitride and gamma ray transform, and this is the early generation of their institute cell in their lab, and later on people started to use synchrotron to do the XRD. And I show you this is our institute cell that I designed in my lab. I started to use it in 2012, I think, when I was doing postdoc at MIT, and then when I started at Georgia, I brought this and also upgraded it, optimized a little bit. So it works very, very well with our instrument. So it's reflective, right? And we put the battery inside. We have X-ray transparent window, and we can collect the X-ray when we are charging and discharging the battery. Okay, so this is what we get. Okay, you can see this is the XRD we get from our material. So what is the difference between this and the result published by Claude Dalmas? Here you have transition. Here we go. There is no fixed transition. There's only solid solution reaction, which means there is only the shrinkage and expansion of the unit cell when sodium going in and out, but there is no fixed transition. Okay, so that means we really realize what we designed. We eliminated the P2O2 transition, and we keep going on to check the second cycle. You can see that the second cycle also no phase transition. There's only shifting of the phase. That's the same phase in P2. Okay, and we are not satisfied. We are not confident yet. So we brought this to synchrotron to use high resolution synchrotron set to check if we miss anything, but we didn't. So this is the counter map of the XRD with just XRD, which is showing another plot of the two cycles. There is only the shift of the peaks, but there is no new peak. All right, and we going on to check the 51st cycle, still the same. That means this material is very stable. We can cycle it for 100 cycles, so still doesn't have fixed transition. Okay. All right. So this is for this material, and so we successfully, we have a theory how to design a better material without fixed transition, and then we verify with XRD and AMR. This is material we get, and they indeed don't have a fixed transition, and that's the reason why we can deliver such high capacity. And so this is our first project, and later on, I think we did a little bit more of refinement and improvement. Refine the formula a little bit and get another material with better capacity retention than the first word. Because the first, excuse me, the first compound is like a proof of concept model, and this one we further optimize it so it can cycle longer with better retention. Okay, so this is the first example that I want to show. How much time do I have? Okay, I think I almost don't have time, but I can very briefly introduce the second project, which we care about all materials forms. Okay, and you may have read a lot of papers. People are making beautiful nanostructures with different kind of shapes, but those projects people are trying to control the morphology, the shape of the materials by just tuning the growth kinetics on different crystalline interactions and facets. But it's relatively rare people are tuning the face itself. This is what we are trying to do. Okay, this is some nanostructure that I did before in my group. But what we want to do is that with the same method, with tuning the surface energy, can we also essentially change the thermodynamics, change the energy of different states? Because you have to have polymorphs with the same composition. You can have different polymorphic phases, with the same chemical composition but different phases. Can we change that by just changing the surface? So with that, we choose a model system which is very simple, metallic cobalt. We choose that because cobalt has two phases, FCC and HCP, but their energy is pretty close. So it gives us a larger chance that we can tune the surface energy to change the total energy. So we first, of course, did some experiments in our lab to show that we indeed can control cobalt to form FCC or HCP with just changing the composition of the solution. Here we just change the concentration of potassium hydroxide in our starting solution. Okay, we can tune it, at different degree for 100% FCC, 100% HCP or mixtures. But we also did computation, DFT computation to try to understand why. And we did calculate the surface energy of different facets of FCC and HCP with hydroxyl group absorbed on it. And with all this energy calculated in hand, you can calculate the total energy and form the wolf shape of FCC and HCP cobalts with different size. So eventually, we have this computational, we call it the nanometric phase diagram. This is different from common phase diagram because you can see the x-axis is the concentration of the solution, which is pH here. And the y-axis is the size of the particle, right, in the angstrom. And you can see that by computation, so if you have high pH, high concentration of OH minus, you got to favor HCP phase. And if you have low pH and lower, smaller particle size, you got to favor FCC. Okay, so this competition result agree with our lab results, but there is potentially a problem because what we calculated here is very small size. This is the nucleation stage. You can see that this is just 1 nanometer. But what we get from the lab here are reactions, are products from reactions 200 degrees C, 20 hours. This is a micrometer size particle. So we cannot directly use this to compare with the computation because they are not the same page. To verify the computation, you have to be able to track the nucleation stage, which is very hard because you have done hydrothermal reaction. You know how it is done, right? Hydrothermal reaction, high temperature, high pressure. So you have to use basically call it hydrothermal bomb, like this thing to do the reaction. And this basically stops you from using any easy characterizations. So we have to design a different reactor to do the in situ XRD to track the nucleation stage. So this is the in situ reactor that we designed. This is force tube. We sealed the reactor solution inlet and we shoot synchrotron X-ray into the tube and we collect the XRD when we heat up the tube. So in this way, we can track the full path from nucleation with the growth to verify, to check if our calculation or our computation is correct. Okay, so that's what we did in the synchrotron. And this is not very easy because we don't have a lot of different time and we are far away from synchrotron. So every time you want to upgrade or test on new idea, you have to wait 3 months. So actually, it's been this project began from 2014 when I started, finished in 2017. So, but we, after we build it up, we use it to check our system. We have, it's also productive. Okay, but anyway, this is the first experiment that we do with this system. We can see now the easier XRD of the formation of cobalt in different conditions. With high pH, you can see that the starting material cobalt hydroxide transformed to HCP cobalt directly, so there is no kinetic effect. So that means this is the thermodynamic stable phase. And if you use relatively low pH, actually neutral pH, you directly form FCC cobalts without HCP. But if you use in the intermediate pH, you form the two phases together. Okay. So I think this is a nice verification of the computation. The direct link the computation and the thermodynamic stable phase. Okay, I think my time is up, so I will skip those things. So basically, our group is material design group. We work on a lot of different custom materials. Recent years, we are working on solid electron materials for oscillating batteries. So you can see that we work on different group of materials, sulfides, oxides, sulfur chlorides, and all the halogen. And we also work on different class of sodium battery materials, anode, cathode, and we also trying to use XRD for in other fields like using in geochemistry with the collaboration with Dr. Tang sitting there. We use XRD to check the elemental reactions. And recently we also developed XRD for electron deposition or electroplating. It's interesting, but I don't have time to do. So I would like to thank you very much for your attention, and I can take the questions.
Any questions for him? I have one about the 2 weeks experiment in the in situ XRD. So you made it sound like, so to speak, easy. So even tempting physicists to try to do that. So, but I'd like to know if it's that easy, and is it an experiment that essentially runs for 2 weeks on the XRD, or when you did the decomposition study? So you had
which one is it? Battery materials or
the first one you showed, so the one which is not solvothermal, so the oxygen.
the battery materials?
Yeah, the battery material.
Oh, it didn't take 2 weeks. Didn't take 2 weeks. So if we do it at synchrotron, is as fast as we want, hours. Basically, is most decided by the kinetics of the material. How fast this material can form. But with lab X-ray, because of lower intensity, so usually we run at the rate of so-called 3/20 or 3/50. So that means the whole cycle will take either 40 hours or 100 hours. So it's not 2 weeks, but it takes a few days.
That's cool, Hailong. So kind of building off that, I also had some sort of a question about kinetics. So when you showed the in situ synthesis, you were saying how it saved a lot of time being able to map out base formation as you heat it up. I wondered to what extent the results you were getting were a consequence of thermodynamics versus kinetics. Are those lower temperatures actually at equilibrium, or are they really phase assemblages that are a consequence of kinetics, like the lithium carbonate melting at low temperatures?
Well, that's a very good question. So I think this question is, would be more important for synchrotron with the X-ray, because at synchrotron people really like to just heat it up, wrap it up in a few hours. So I would argue that what you see is really the kinetic effects or thermodynamics. But with this result ran in our lab, so what we do is that we ramp up to one temperature, and then the scanning time is about 1 hour. We stabilize it for maybe half an hour, and then run the XRD for 1 hour. So our time, of course, we cannot see this absolutely no kinetic effects, but mostly I think it is close to the kinetic. I mean, some of that is pretty.
So if you cool down, repeated the temperature profile in reverse, would it reproduce down to the temperature at which things, obviously you decompose your carbonates? Would it reproduce over most of that temperature range on cool?
We did try quite a few samples, because we also care about what's happening during cooling. Because the materials we got from after cooling is the material that we really use in metrics, right? But I would say half and half. Some material, we even cool it down and repeat it up again and cool it down again, do a few cycles. Some material repeats itself very well. So you always see the same transition at the same temperature, but some doesn't. As you cool it down again, different stuff.
Right. In the interest of time, we'll close this talk. Thank you so much, Hailong.